Okay, so I guess we can just start. Let me see. So today we'll cover the topic of lighting mostly. It's also a very important topic when it comes to getting the impression of 3D, because how light is bouncing off surfaces is really giving the impression of depth and those sort of things. So it's quite a long lecture, so I decided to divide it into two basics today. Certain algorithms that is out there, and then the next time we'll talk about more code-related stuff, probably together with the lab following. But first, there will be some more general information. Let me see. About the course. So there's some important things we need to mention now. So we already started assignment 1. I cannot overemphasize starting early there. It's a hard deadline on the 3rd of March, as close as you get to 12 o'clock in the evening. If you uploaded your assignment before that point, then things should be fine, basically. And as we talked about on Tuesday, the idea is to get some core things up and running, and then you build all the fancy stuff afterwards. It's easy if you do too many things at once and it doesn't work properly. It's hard to figure out what went wrong. So it's nice to just have an executable that we can evaluate for you, basically. And there will be a presentation the following week, either that Thursday in this room or the week after. We can decide on that later. And next week we will basically we will have no lecture on Thursday because it's the skiing day, and on Tuesday we will solely just use for assignment 1, taking questions and those sort of things, so you get going early. And you have 2 weeks left, so we're sort of emphasizing that instead of moving that forward, because when you have just 1 week left, it may start to get a bit heavy to start that late. So next week we can basically dedicate to assignment 1. Now assignment 2 will start basically right after assignment 1 is finished, and you will have about 1.5 months on doing that. And the reason is that it counts a lot on your grade. It's about 30%. And secondly, when you put up all the framework you need to solve that task, you're basically ready for the exam. So the exam will basically be using some of these things again, solving a slightly different task. So in a sense, assignment 2 becomes exam preparation, and you will have a lot of time on that. There will also probably be around the 24th of April that will be the deadline for that, and there will be also a presentation on that closely thereafter, basically. And then the exam. If you go to the times or the information for the course, you will see that it's basically already set up. So it's from the 18th to the 20th. So I usually have these goals is that you get this task on the 18th, and then you have 3 days to work on this at home, or you can sit here or whatever. After 3 days you should have been able to finish this thing up. Then a week or so after that, you will be asked to give a presentation on this subject, basically. But this exam dates needs to be set. I don't think we are really needed to, if we get to May 2020, this is basically the dates that are set on the webpage already from the examination office. And but since we don't need any censors or anyone to guard the exam, or we don't need to approve the task and so on and so forth, we're free to move it a bit around. And what they've done in previous years is that they had it during a weekend, because during the weekend there are less people here, and there are more group rooms that people can have if they would like to, discuss and those sort of things. So that's an option if you're interested. So the question is, there are basically 3 alternatives, or 4. The one that is actually set already. Then of course it's these 3 first weekends in May. We don't want to put it any later than that, because there will usually be some time from you deliver your task until you give your presentation, and if you start to get into June, it's getting late. So. And also it's quite nice to have it relatively close to your delivering assignment 2, so you're basically within this thing. I guess maybe the first weekend, since you may have a presentation, this week will be a bit close, so maybe these are the best 2, or we can keep it at the days that are set. That's really up to you. But there needs to be a consensus. We won't operate with several ones, so everyone will be given this task in a typical days, basically. So, any particular interests? Would you like to have it as it is, or move it to some other weekend?
Which is also like I have to look at my other exams and how to
Yeah.
match it. Don't remember my exact exam date, so can't respond.
Because the problem may be that someone has seen this and then they think, okay, now it's scheduled, everything is fine. If we then switch, everything is messing up. So if someone doesn't have possibility to do it there, let's say they have an exam on Friday or the Monday after, then it will not be convenient, and we have to make sure that it's convenient for everyone. So maybe in that sense it's best to operate with these days. But I will try to. I can put out this doodle poll, and during next week, and then in 14 days we can just go through it, and if everybody votes for a different alternative, choose that one instead. Otherwise, we'll just keep it as it is. So the important thing is that everybody's capable of being present and doing it in those days, so that you get the possibility to deliver the exam. Okay? Any questions around that?
Also, the exam is individual, right?
It is individual, but you should deliver your individual task. But I mean, as it's a home exam, we can't be a control that you're not collaborating, so it's open to discuss with others and so on and so forth. But if we see that some delivers very similar code, it's unlikely, so then you will get stressed a bit on the oral exam afterwards, and we will see whether it's really your work or somebody else's. And of course, if you discover that it's not, then that's not going to count in the right direction. So I think it's open, basically, because of this fact that you will probably write something a bit differently than someone else.
And what will it be like? Create certain shapes and do this and that and lighting, or what kind of examples? Like, what will the exam be?
It will be covering most of the basic things that we've been through. And assignment 2 will be about combining many of the things we've seen right until now. Basically, most of the components. So the lectures I've been giving until now, they will definitely be covered. The ones I will give afterwards will also be covered. We will have some additional lectures, because we will probably have time for that, where we talk about other things related to computer graphics and sort of expands the horizon a bit. Those things I think is more optional. They will not necessarily be part of the exam, but it's just for curiosity. And maybe there will be a talk by Carl about drawing, drawing in different ways, because he's very good at that task. So his knowledge in that would be nice to communicate, and that may be useful, for example, during the exam. But we'll see what happens once I cover all the necessary topics, and they will at least be part of the exam. And then, Any other questions? Okay. So then today's talk, lighting and colors.
Oh, I actually have one. Do we have like a previous exam that we can look at and practice on?
Maybe. I will get back to that later.
Right.
I'm not sure what they've been operating with before, because it's basically if you have solved assignment 2 properly, then basically you will have the tools you need, and it will probably be quite different from what you see in other years. Maybe have some of the same components. So I can get back to that closer to the exam.
Yeah.
Okay. Now computer graphics. Often in computer graphics, we want to simulate how the real world actually looks and make it look realistic. Sometimes you don't, but in many cases you want to do that. And to do that, you need to understand what really happens in the real world, right? So you're a bit down to physics. Now, until now, we basically talked about how you create triangles and polygons and those sort of things, how you can color these surfaces, how you can put textures on them, and so on and so forth, and also how you can move them through space. These are very important things, but if you really want to get into the 3D of impression of things, lighting is really important. It's just by looking through this room how shades are cast, for example, when you have a light source and those sort of things. You can basically cover one of your eyes and you will still have the impression that you're in a three-dimensional world. That's really up to how light is bouncing off surfaces. So you can also use, go the other way around. Is you can take a picture of the room and you can try to create a 3D model from it based on how light is bouncing off with certain knowledge of material properties and those sort of things. So the talk of today will basically be physics. I will not go into very heavy stuff. I'll try to keep it a bit superficial so you basically understand what we're talking about. And it will basically be connected to colors and light. Yeah. First, just to have a little discussion about what color really is. So, if an object has a color like this apple here is red, it's not completely red, but let's say it is for the discussion. Now, is that universal, this red color of something? Or is it something else to this? Anybody thought about that? Yeah.
Well, it's not universal because light is just color is just a perception of different wavelengths and physics and stuff.
Exactly.
So basically, it depends on how you interpret that specific wavelength of light with your eye.
Yes.
If you're colorblind, you might see a different color.
Exactly.
But that color's wavelength is universal though.
Yes, that for example, a wavelength of 650 nanometers you will perceive as red in most cases. Of course, the big question is, does everybody see red as red? Or does somebody see red as green and then call it red? That's the question. Some brain research actually points towards everybody's having the same perception of red. But maybe everybody likes the same color, it's just that it's changing in different brains for all that matters, and then everybody likes green, but it's actually looking red for something, so on and so forth. But it's most likely that you have more or less the same sort of label put to the wavelength of, let's say, 650 nanometers. Any other things that will affect the color? That's one very important thing. It's actually what color is, basically. It's you don't really have the colors in the outside world. Can anybody imagine what is universal for the object?
Shape.
Yes, shape is one thing, but when it comes to the color reconstruction, of course shape matters because you will get some shading, but let's say it's just the surface that is red, for example.
The way the light bounces off.
Yes, exactly. So the material properties will really decide what you will see and what you will not see also. And the last thing is
The amount of light, probably.
yes, in a sense, or the type of light or the frequency that the light covers. So the light source, basically, what it consists of. So basically, yes, there's really no universally red. What is universal for an object is basically how it absorbs and reflects electromagnetic waves. Then, of course, the color will depend on your illumination. If this was just a blue light, the apple wouldn't appear to have any color at all, for example. But the most important thing is out in the world, it's only electromagnetic waves or photons bouncing off surfaces, right? And it's, as you said, it's in your conscious perception that the color red is really happening. And that's really an interesting problem in itself because it's really unknown why we see these things in that way, why there is anything at all. Purely physics, you could just say, well, if you're a robot, you can take in 650 nanometers, and you'll be fine with that. You'd call that red, but you wouldn't have any conscious perception of it. Yeah. The fact that we have this conscious perception is a really hard problem that is more or less unknown why this thing happens, and it still is actually. So it's very interesting. You could have a course on that as well, but that would cover a course of its own. So I will not dwell more with that. We will mostly deal with light sources today and the physics of objects, and then we will just assume that the brain is what it is and does what it does, and put these labels on, given that it's given a certain input. Okay. Okay, so lighting, of course, already what we said. If you don't have any light at all, then of course you don't see anything. Of course, if the surface is glowing, it's also emitting light, so it's all back to that. So we see them because either lights reflect on them, or, as I don't really mention here, is if they are glowing or emitting light themselves. So brighter light makes brighter colors, for example. The angle of light and how it bounces off the surface, how it sort of is related to the normal of the surface will decide how bright the light looks. And colors, I don't know if you see it here, will of course look different under different light sources. So for example, on the sunlight, it's the most ideal light to have. I'll get back to that soon. If you look under a normal light bulb, it has more of a yellow tint to it, so it will look a bit different. But still we're able to differentiate them from each other, which is a good thing, of course. Yes, of course, when you're lighting objects, one thing is, which is also very important for the perception of the 3 dimensions, is that you have shadows. And to make it realistic, you will have different shadows. If you're shining a very bright light source towards some objects in one direction, then they will cast quite hard shadows because light travels in straight lines. Or at least they follow the lines of the space you're in. So if space is curved, then you follow the curved line. But these are other things. We can assume flat space, so they travel in straight lines, and therefore you get these hard shadows. Now if you put this object here in a room like we're in now, you may have a shadow from the direct source, but light will also bounce off any other surface, right? So it will be lit from different angles, and then you'll get softer shadows, right?
Compared to your own shadow, when you go closer to the wall, it becomes harder, and if you access that water, it gets more own shadow.
Yes. And that's probably because if I'm close to here, I will, light will be more directed towards me. If I move around here, there will be reflections coming around and making it appear a bit less hard. Another thing, for example, if you have a white room and you just have a light of a certain color, that room will appear to be colored in that particular light. Of course, if you have a different colored surface, it's not necessarily like that, but the room will basically change its appearance depending on what sort of color you light it up with. So to the electromagnetic spectrum, I will not dwell too much with it, but it's quite broad. It goes, just a little repetition from physics. I guess most of you know what wavelength is, but just in case I can repeat it. So an electromagnetic wave is basically an electric and magnetic field that propagates in space. So it actually has a spatial extent. And you can very simplified draw it as a sine curve like that. It doesn't necessarily look that simple, but let's say it does. And then this propagates in time also, but it has an extent in space, so this will propagate along all the spatial axes, x, y, and z. We just draw it in the x direction now to keep it a bit simpler. And the wavelength, of course, is the distance from one peak to another in space. Now with electromagnetic waves, it's quite simple because they all travel at the same speed, which is huge. It's like, I think it's 0.3 billion meters per second, or 3.6 billion kilometers per hour, which is like unimaginable speed. Nothing else in the universe moves faster. It's basically the upper speed limit. Nothing else can reach that one, at least if they have mass. And that wavelength is also, of course, connected to a frequency, because you can turn this around and say how many periods per spatial unit you have, how many periods per second you have due to the frequency. And they're related through this. Since this is a constant for electromagnetic waves, and basically that you have this relation between them. But we're mostly interested, so the wavelengths ranges from kilometers or hundreds of kilometers up to very, very, very minute small distances. In this course, we're interested in what we can see, and that's this pretty small little wedge, wedged in between. It's very, very small little band between ultraviolet and infrared, which basically covers all the colors we can see. And of course, mixtures of these, which is not really covered from these particular wavelengths. So they usually span from around 380 up to 750 nanometers. And we usually express these waves in nanometers and use the wavelength instead of frequency, usually because the frequency is so stupendously high that you really don't have you have a name for it, but nanometers is more like a common name, and it's numbers that you sort of at least are a bit used to be with micrometers, nanometers, also so forth. So nanometers is basically how you say you have a color of a certain wavelength instead of saying you have a color of a certain frequency. But you can use both. Right. So this is basically what we can see. Any questions to that? Okay. Now, so to the different lighting models. Sunlight is the most ideal of all. It basically sends out energy in all of the visible wavelengths. I mean, basically a whole frequency band, but it basically covers this in a more or less flat way. It's not entirely continuous. There are some absorption lines due to the atmosphere of the sun, but they're so minute you can approximate it as continuous. It's mostly the most ideal light source we have. So when this one is bouncing off any surface, you will have the most, right perception of color for that sort of surface. And of course we have man-made light, and it's usually never that ideal. You have what we call incandescent light. It's basically light from heat. So you send current through a wire and you make it glow like in your light bulbs. They're basically also having a continuous spectrum like the sun, but it's not flat over the whole. Let me just draw this. If this is your electromagnetic spectrum, this is the energy, and this is the wavelength, and let's say this is the visible range, then basically sunlight is covering this in a more or less flat way from red over to violet. So equal energy in all of them. Now these man-made lights, they may, for example, start at a bit longer wavelengths and then sort of cut off at some point. So they look a bit different. They don't cover all the colors in such a nice way. So for example, if you look at incandescent light, typical light bulb, it will cover the frequencies like that. Actually, you have most energy in the infrared, which is why they are hot when you touch them, because it's basically heat radiation. And then you have less blue than you, for example, have red and green, and that's why they appear a bit yellowish when you look at them. But they're continuous. And then you have this other type of man-made light, which is basically luminescence. They usually have these bands of the electromagnetic spectrum. So it's like they just emit light in certain fixed frequency bands, like this one and that one, something like that. And you may make this one appear white as well, because you just to get white you need to basically mix three primaries, red, green, blue, as we see in this course. But it's not ideal when you shine on surfaces where it doesn't really cover everything. They will look dimmer than they would, for example, on the sunlight. So you get color changes when you use these sort of light sources. And these light sources looks this way because we make these light sources from different chemical compounds. And if you look into quantum mechanics, each and every substance in the periodic system will have their own light signature. So you can basically identify every element in the periodic system from the light they emit. If you bombard them with, for example, electrons or photons or something like that. And what we do when we make these LEDs or sodium or xenon lamps, or we use gases in tubes, is that we put in a certain substance, and that substance will have a spectre, and that will basically just pick out some of these ones. But they will not get hot, as for example the bulbs do, and that's why we have started to shift towards other types of lighting now, because you waste a lot of energy just throwing all this energy from heat radiation on these light sources. But you don't necessarily get the same sort of light as you may have experienced. If you have changed from a normal light bulb into LED lights, for example, you will see that there are differences in how the room looks. Yeah, it's just a little picture of I think it's a glowing wire in an incandescent in a light bulb. So, incandescent light is continuous spectrum, but it usually has a cutoff. It shapes the frequency spectrum in a different way than the sun, and you have this luminescent light sources that has this white spectrum. Now there are different ways you can so-called dope these different chemical compounds so that they get broader spectra and so on. So I won't go into details to that today, but this is the main difference between incandescent and luminescent light sources. Any questions on this? Okay. So over to human perception. That's of course a very important part. I said I wouldn't talk about how the brain represents colors, but I will talk about a little bit about the retina. So inside your eye you have light coming in, right? So if your eye is here, basically you have light coming in from all directions. It goes to a focal point in your eye, and then it's projected onto this little surface on the back of your eye, basically. And that surface consists of neurons, 4 different types of neurons, which are light sensitive. And of course from here they send these signals back to the brain. And you have rods and cones. Rods are basically the ones that is a bit outside of the focus of where the light lands on the retina, so it's more on the circumference of it. And it's what you usually use when it's little light available. So for example, if you're in a dark room, or if you have a walk in the forest at night or something, you get night vision. And that's when basically you see your rods working. And they basically don't have color, it's more grayscale. And then you have the cones, which is basically more what you use when you look in broad daylight, basically. And they have 3 types. You have blue cones, you have green cones, and red cones. Roughly speaking, these cones are sensitive for red, green, and blue. But as you can see from these curves, for example, the red cone doesn't have a spike at this part of the spectrum, right? So it's not just sensing red. It's sensing something that is a bit shifted down towards yellow, so it's actually, orange-ish like. And then it covers a little spectrum, so it works more like a filter than it works like just something picking out a particular frequency. So back to what I talked about last time, touching upon filters is basically meaning that it picks up a bit larger chunk of the frequency spectrum than just red, for example. And same with the group green and blue cones. And I think this is also the reason why we usually choose red, green, and blue as primaries for our spectrum, because it covers its spectrum with quite a similar distance, and it's sort of corresponding to also our perception in a sense. But the point is that each type covers a different frequency range, and together they sort of cover the electromagnetic spectrum in the visible range. Any questions, comments to that? The fact that these curves are not as ideal as spikes, for example, is one of the reasons why color science is getting quite interesting. But not everybody has these all these 4 sensors. If you have 3 cones that can see colors, you basically call it trichromat, meaning that you can see 3 colors basically, and you will have the possibility to see the diagram over here. Anybody here who is colorblind? Dichromats, monochromats? Okay, so anyway, a dichromat means that you lack one out of the 3 colored cones, right? So for example, if you lack the ability to see green, you will see this color chart here as the one right up here, right? And if you lack the red, you will see that one in the middle. And in both of these cases, you have troubles differentiating between red and green. And the last one, if you lack the blue, you'll have problems differentiating between green and blue, and so on and so forth. And then, of course, you may lack alpha, you'll just see in grayscale. And there are different ways of dealing with this called atomization methods. One they work on here, they have large research projects on color and color science, and one of the projects is basically how you could make people, for example, wear some glasses or take pictures of the world and be able to differentiate things they could not differentiate otherwise. So, for example, if you elect the possibility to see red or green, you get this red-green confusion. So these bands you see here, the red and the green one, will appear almost exactly the same. But you can do certain signal processing techniques, shift things around, so that you end up in, for example, this case. So you shift the colors, so you're capable of differentiating between them. These are techniques that are available. You can do other things like put in patterns and those sort of things, but it's a bit disturbing. If you could basically just shift colors, so you could look at this through some camera or something, and then, for example, be able to say whether red berries are on the ground or they're green. for example, if they're ready to pick, you could just use this camera and you could figure out, oh yeah, they are, because the berries have this sort of color compared to the green that it would actually be. So there are ways of dealing with this in signal processing or in image processing. Okay, so a bit more over to the color science. Now we already seen when you mix light, we use 3 primaries. Well, primaries are basically the name for the 3 basic components we use, like the colors we use to mix out and get all the other colors. So when you mix light, you have so-called additive color mixing. So this chart up here is basically what we've been working on in this course already. When we set the colors, we basically set red, green, and blue, and we get. It's called additive because they add up to white. So when you add more, they become brighter and brighter, and you end up having the white in the middle there if you add all 3. So this is how light mixes, basically. So for example, if you have mixed green and blue, you get cyan, and if you mix green and red, you get yellow, and so on and so forth. So that's nice. But if you remember back in when you were younger, maybe in kindergarten or in the basic school, you were given these paint kits where you could mix different colors and so on and so forth. And I don't know if you remember how you did that, but it definitely did not work in this additive way. It was a very different way of mixing colors. So if you want to mix paints now, for example, you don't mix it after the additive one, you actually use this chart here, which is different. So when you put paint on a surface, the mixing is different, or you use different primaries. For example, if you look at the print cartridge, you will see that you have magenta, cyan, and yellow instead of red, green, and blue. And some may even have learned that at school that, well, the primaries for mixing paint is red, blue, and yellow, which is not true, at least as long as you use red, green, and blue for primaries of light. So that's what I learned. If you mix blue, red, and yellow, you get all the colors. But that's basically wrong. The right is you have to mix magenta, cyan, and yellow. And why is this? Why do you have different primaries for having mixed paint you put on walls compared to having mixed light? Any idea? Yeah.
Because light is emitted through an absorption spectrum.
Yes, exactly. So basically what you put on the wall is absorbing light and reflects. It absorbs what you don't see and reflects what you see. So if you shine white light on this surface, that's actually not a good example because the surface is entirely white. Okay, so let's say you shine it on this one. Let's say this is blue. Or let's say it's cyan just for the sake of it. Then what color does this material absorb?
Everything else.
Yes, everything else than cyan, which is
Yeah. Everything other than green and blue.
yes. So it's basically if your light is you're basically removing the red out of the red part of the spectrum out of the mix, basically, and you end up with something cyan. Same thing is if you see a green surface, it's because you have removed the red and the blue, or the magenta in a sense. So that's the important part. Of course, when you mix light, basically you add them together. When you put paint on the surface, you subtract out certain colors because you see what is reflected and you don't see what is absorbed. And it's not a coincidence that you see the same colors within here as you do on the primaries outside in the big circles, right? So the primaries in the subtracted case are basically the one you get when you mix 2 and 2 of the primaries in the additive case. And therefore they call them complementary colors. And they're also called subtracted because you subtract them out. If you have all 3 of them out together, you get something black and you don't see anything. Right? That's the opposite to light, where it gets brighter and brighter when you mix them together. So, why are they called complementary? Well, let's say this is your surface now. And it looks cyan, like this example test. It's because the red part of the spectrum has been filtered out. So in a sense, you can see you can see your surface, or what your surface absorbs as filtering out the part of the spectrum that you don't see. So in this case, with these seeds, you don't see the red. Or if you had a magenta colored surface, like the one here, it has basically filtered out the green, or if it's yellow, you basically filtered out the blue. And the opposite way, if you see blue, you filtered out the yellow part, and so on and so forth. And they're called complementary, because if you add this primary for the additive case to the primary for the subtractive case, you get a flat spectrum and you're back to white. So this is why we use that name. They sort of complement each other. So absorption and reflection is really the key. Any questions? Okay. So let me see if the stream is running. Good. 51. Okay, we have 10 minutes. I guess I can start to introduce this rather nasty equation then, which we have to do since it's graphics programming. Anyway, okay. You have something called the rendering equation. Now, what is that? First and foremost, I said the equation I show now is not the one you use directly when you try to render some scene. You use approximations to it. The equation I'm going to show now is basically a quite physically accurate description on how light bounces off points from a surface. And it looks pretty nasty, but this basically encapsulates most of the things you will see given some point with light falling onto it. So if I would like to consider this surface and how it would reflect light, I would have to consider all points on the surface like this. Now I'm just considering one point basically. And at each point you have to do this on any surface you would like to render if it should be physically accurate. So what are all these things? Well, try to illustrate with this illustration on top there. So from your point you have some incoming waves, which is W with this mark on it on the top there, or W prime. And I've drawn several blue arrows because you will actually like to consider all possible incoming directions of light. And what you see is, of course, what is reflected to your eye, this W there, the orange arrow. And how strong that will appear will depend on the direction of the light coming in with respect to the normal vector of your surface. I'll get back to why that is the case soon. So what you do end up receiving, the light that is reflected off the surface, or the color you will see, will depend on all these incoming light rays. It will depend on whether or not this surface emits any light itself, whether it's glowing or not. And you would like to consider all different incoming rays. So you basically take a sphere around your point, and you will get all incoming rays to evaluate that particular point. And then you sum all the contributions, which is basically this integral. So let's just take it part by part. The light output at the point of the surface, basically what you see, is this term. And it is actually multivariable. So you have first x, which is the position in space. And then you have omega, which is yes, outgoing direction. Then you have lambda, which is wavelength. Think about when you hit a prism with white light, you will get different colors reflected in different ways. So it is dependent on the wavelength and also time, because this is changing over time. Yeah.
What was omega again?
Omega, yeah. It's the outgoing light ray basically. So it's a vector. I think it's a bit misleading to use omega there, because sometimes you use omega to denote frequency, but again that's what how this profile was put down on these slides probably should be changed. But anyways, it's the outgoing vector which you see. So can anybody imagine what this first constant term may be? It's something we don't sum over. If you look at this picture, we have all the incoming waves being omega prime. which we basically sum over all by this integral. And the idea what this constant term would
Something involving white light?
Hmm?
Something involving white light?
Yeah, it may, but not necessarily. Yeah.
Maybe it's something like the properties of the surface,
Yes, you're onto something. Yes.
like something that is independent of that point.
Yes, and independent of the incoming light,
Yeah.
which would be
Reflective and
well, if it's nothing reflected off, then it's basically not what's coming in. But it has to do with the surface property, exactly like you say. So what may it be that adds on to the light that falls out? If it's not coming from incoming light, where would it come from?
The surface
from the
itself.
surface.
Surface itself, yes, exactly. So if the surface is heated up or is glowing, emitting light itself, you have this constant term to just take that into account. The rest of this equation is about light that sort of comes in, which is absorbed or reflected, basically. And there you have many terms. First and foremost, you have which is called the BRDF function. It's basically a bidirectional reflection function, it's called. And it's basically taking into account the properties of the surface, how it reflects or absorbs light, basically. So this tells you about the physical properties of the surface. You can have many different functions there, but we just take that one for now. And of course you have the incoming light, and both of these are also function of the incoming light wave, double prime there. So you have that one, they're put together. Let me see. Oops. So incoming light times the reflective properties of your surface to tell you how much is sent back to the observer. And then this term here. Anybody who can see what that means?
What's the normal of the surface?
Yes? And
yeah. That's the dot product.
it's a dot product, yes, exactly. And what does it do? It scales the whole thing. So you have how much light is reflected off the surface, you have the intensity of the incoming light, and you also have this term which will scale it up and down. So just to draw it here. This is your surface, this is the surface normal. Here's the incoming light vector. You have an angle theta between them. So basically, if I go one slide ahead, you can see, oops, what it is. If you hit your surface with a flashlight directly, you will reflect everything back. If you hit it at a 45-degree angle, it will smear out a little bit so it will look dimmer. And if you tilt the angle even more, it will look even more dim, right? And if you just put it parallel to the surface, and either you don't see, really no light is reflected off the surface because light travels in straight lines. And that you can formulate by this famous dot product that I talked about earlier. Where the dot product is basically n times w. You can say it's equal to the norm of these two vectors, which is basically the length of the two vectors multiplied, and then the cosine of the angle between them. And it's basically telling you how much of one vector is pointing in the direction of the other. And of course, if they point in the same direction, this becomes maximal. If they are at 90 degrees, then no light will bounce off the surface at all, it will appear black. And if these are normalized, so they have unit length, then you basically see that this product will be equal to cosine theta. Or in this case, since the vectors are pointing in different direction, it will be minus, basically. So that's the last term of this equation. And then you have to do this for all the possible incoming rays, which you do by just summing them all together. And since you have an infinite number of possibilities of incoming rays, you will integrate instead of summing. And then you'll get the...
When we are going to work with light, do we have to put this in the code, or does GLM input has a function?
But this will, thankfully, you will not have to deal with this one anymore, actually.
Okay.
Because this is the physical accurate description of how light is bouncing off surfaces, right? But it has the necessary ingredients. It has the emission of light, it has the reflective properties of the material, it has the incoming strength of light, and it has the incident angle. Now these four we will work on, right? But we won't work on it in that sort of detail, because now I described one point. On your surface you may have, hundreds of thousands of different vertices, and calculating this thing would, I don't think you have computers that does that. So basically this is just to have the physics of it all. This is the exact physics. And now in the next hour I'll talk about algorithms that try to approximate this formula. First, some algorithms that you could use if you do offline rendering, which is something, if you don't do professional rendering, you make movies and those sort of things. And then I will talk about what we're going to use, which is a very simplified model, not very physically accurate, but which looks appealing, basically. But it all comes back to trying to put in these components of this equation some way or another. So, yeah, you may forget about most of this, except for the fact that it has these sort of different things we need to take into account to make it look, rather real instead of superficial. Okay, so I think it's time for a break there. Take 15 minutes.